Okay, so the title of the talk has been given by Janani, exploring the El Nino climate phenomena using data-driven methods of eigenvalue statistics and network theory. So essentially, I'll be trying to understand a climate phenomena, El Nino, called El Nino, using statistical eigenvalue statistics and network theory. That's basically the idea. And I'm doing this in collaboration with my very bright student, Pooja Jain. And she is my second last student. I have another one. And here's the climate phenomena. So I'm sure that lots of you don't know what the El Nino climate system is. It is basically an unusual increase in sea surface temperature in the Pacific Ocean. And here's a diagram showing normal conditions. Here's the heat, it's the Pacific Ocean, and the water is getting heated up. Okay? And your rain is happening here. Okay. During the El Nino, what happens is that the sea surface temperature increases, and so the low pressure region shifts and the rains happen on the side of South America and Americas, okay, instead of near Australia, etc. Okay? And this occurs every 2 to 5 years, as shown in this timeline of the episodes from 1900 to the present. Okay? It occurs every 2 to 5 years. Okay? And it disrupts the normal weather patterns, as I explained. Okay? So the rains happen further down. And this causes floods and droughts and storms. And also because of this, the heating of the surface temperature, the coastal fisheries also get affected. So this is the thermocline line. And in the normal conditions, there's lots of good fish here. But during the El Nino, because the thermoline decreases, the fisheries become less effective. Okay? And as a matter of fact, the El Nino phenomena was discovered by a young Peru fisherman who was in the Pacific Ocean at that time. Okay, so why study El Nino? It's very hard to predict because you see it's happening very irregularly, okay? But it occurs every 2 to 5 years and affects a lot of people. And the traditional methods miss the complexity of these connections. So we are trying to help in this direction by using data and statistical approaches to identify patterns and key signals. So we use the method, as I mentioned in the beginning, the method of eigenvalue statistics and network theory to understand and predict these patterns of the El Nino. So we take the data, okay? We take it from the ERA data from the climate data store, which is this ECMWF. And for the years 1940 to 2024, and we take the temperature and on a daily basis. Okay, in the bank, the resolution of the data is 0.25 in both the latitude and the longitude. Okay, of the Earth. Okay, but because the phenomena is a specific one, we have limited our region to between 30 degrees to 30 degrees north to 30 degrees south, and with a resolution of 7.5 degrees, which is scattered homogeneously. And here are the 136 geographical locations that we have isolated to study this phenomena. Okay. So the method we use is to study the correlation coefficients, or the Pearson correlation coefficients, of the temperature anomaly, Okay, the temperature anomaly is not quite the temperature, okay, and I won't go through the details here, but it's basically we are studying the correlation function, okay, for a period of 1 year. This Y represents 1 year between two nodes ij, okay, the nodes being the geographical locations. We study the eigenvalue statistics of this correlation coefficient, as well as make networks. Okay, the networks, in networks we have these nodes, and the edges are made from the nodes I and j if the correlation coefficient is greater than or equal to theta, which is the threshold, and we select a threshold of theta greater than 0.2 using random matrix theory. And in particular, we use the theta equal to 0.3 because of visualization. So here is the climate network. And this is for the El Nino year 1982. The normal year, the climate network is given in this way, and you can see it's quite densely connected, both in the equator as well as the tropical region. And the indicator year, 1981, you see the connections dropping drastically. And then in the El Nino year, the connections come back, okay, from the equator to the tropical regions, okay. And this is repeated for this El Nino year 1997 and all the El Nino years that you see, okay, especially the strong ones, very clearly seen. And if you look at the properties of the networks, like highest node degree, total number of links, and clustering coefficient, you find that for the indicator year, the properties decrease and then increase for the El Nino year. And this is a table showing that. The total number of links, highest node degree, clustering coefficient, that's what's happening. Okay, so these are good indicators. Okay, so now let's turn to the eigenvalue statistics. In the eigenvalue statistics, what we do is find out the eigenvalue, okay, the eigenvalue distribution, and look at the outliers. The outliers are those which are beyond the random distribution, okay. In this case, there is the largest and the smallest eigen values of the random distribution, okay, and these are given by the red lines, and the outliers are the ones that are away from it. These are the ones, the top outliers, and these are the smallest outliers. A few minutes. Okay, so this is an indicator actually, in which if you look at the number of eigenvalues that pop out, okay, of the when you go from one year to the other, you find that the number of eigenvalues outside the bounds increases in the El Nino years. That's what's shown over here. Okay. And it's found that the smallest eigenvalue using the inverse participation ratio and Shannon entropy are the most informative. And if you track the smallest eigenvalue for the various years, you find that the El Nino occurs the indicator year. The indicator year has high smallest eigenvalue, and the El Nino year is low. Oh, I can't. Okay, the El Nino is lower. Okay, and if you look at the square of the eigenvalue components, okay, in the indicator year, you find this sort of a bump at 75, which is the equator position, and these are the tropics. So you find that a lot of the components are at the equator and a couple in the edges. Okay? And a similar thing happens for the El Nino year, and so it turns out that these are very important for the El Nino phenomena, and controlling those positions, you can control the El Nino. Here is another diagram, which I'll just go very fast over, in which you're looking at the second smallest eigenvector, and you're not looking at the square. Okay, you're looking at just the components. And you see that if you look at this color code, you see that the blue and the green are sort of near zero, and the red and the purple are larger. So in the equator, you see the components in this manner in the indicator year. But if you look at the El Nino year, if you take a look at, concentrate on this one, which is a blue or a greenish color, it becomes a red one. So from an indicator year, it's flipped sign. Okay, so this is a very important indicator of the El Nino, and it tells us the very important geographical locations that we have, and that is what needs to be controlled. Okay, and so the take-home message is that random matrix theory and network analysis helps understand and predict the El Nino, and which shapes the global weather. And yeah, so this is very important because we need to have better weather prediction methods for the El Nino. Okay, so here's the acknowledgement, the references, and I thank you. Thank you very much for your patience.
If any questions?
Yes. Did you say this doesn't happen in Indian Ocean? This is in the Pacific Ocean.
This doesn't happen in Indian Ocean?
It affects it affects the Indian climate. I mean the monsoons. It affects. There's droughts when El Nino happens in the Indian continent.
Whether such phenomena happens in this region?
In India, in the Indian Oceans.
Right. Or don't we have any data?
I don't know if we have. Yeah, it's very difficult even to get the monsoon data. The climate data. We would love to do that problem also. Thank you for the question.
So is this year indicated year?
Yes, it's been indicated by this analysis. We indicate that El Nino is going to happen. Though La Nina, which is actually the opposite of this, that means when you have a cold thing, instead of the surface temperature is cold rather than the hot, this method predicts both of the things, the La Nina as well as the El Nino. And it's predicted the El Nino for this year. Yeah. Thank you.
Let's thank the speaker.